You ever just stop and think about the tiny lights that are, well, literally everywhere? I mean, they're in your phone, your car, your TV, your house. LEDs, light-emitting diodes, have completely taken over the world. But here's the thing. They're not just tiny light bulbs. Nope, they work on this absolutely fascinating principle of physics that lets them create brilliant light without, just burning up. So let's get right into that, because that's the real question, isn't it? How does this little chip of semiconductor material create so much light so efficiently? And what's stopping it from just cooking itself? Well, the answer involves a pretty epic journey at the subatomic level, a great escape, and an unsung hero.
And believe it or not, it all starts with something you can actually picture in your head. At its core, an LED is basically a sandwich. Yep, a sandwich. But instead of bread and fillings, we're talking about some very special, highly engineered materials. So that sandwich is really a special kind of semiconductor diode. The name itself, light-emitting diode, gives us a massive clue. To get the light-emitting part, we first got to understand the diode part.
Okay, so think of a diode as an electronic one-way street. That's it. It's the most basic building block in modern electronics, and its entire job is to let electricity flow one way, but slam the door shut if it tries to come back the other way. This one-way street property, it's the key to everything that follows.
So how does it create that one-way street? Well, to find out, we need to zoom way, way in and follow the journey of a single electron as it travels through the very heart of the diode, a place called the p-n junction.
And here they are, the two pieces of bread for our sandwich. On one side, we've got N-type material. It's been doped, which is a fancy way of saying engineers added impurities to give it a bunch of extra free-roaming electrons. On the other side is P-type material, which has been doped to create lots of holes. And you can literally think of these as empty, electron-sized parking spots just waiting to be filled.
Now, the second you press these two materials together, something really cool happens right there at the border, at that junction. The free electrons from the N side immediately jump across to fill the nearest holes on the P side. This creates this thin, neutral barrier right in the middle called the depletion zone. It has no free electrons, no open holes, it's perfectly balanced, and it acts like a wall, an insulator, stopping any more electricity from flowing.
So, how do we get things moving again? How do we break down that wall? It's actually pretty simple. We apply a voltage. We hook up the negative end of a power source to the N side and the positive end to the P side, and that gives the electrons a powerful shove. This push is enough to shrink that depletion zone, letting the electrons surge across the junction and into the P-type material. And just like that, current starts flowing.
And right here, this is the magic moment. As each of those high-energy electrons from the N side finds an empty, low-energy hole on the P side, it falls in. But you know that extra energy it was carrying has to go somewhere, right? So the electron releases it in the form of a tiny particle of light, a photon. Billions and billions of these little events happening every single second create the steady, bright light that we see.
And I love this quote from our source material, because it really drives the point home. The light isn't created on the surface of the chip, or throughout the whole thing. It's generated only in that incredibly thin junction layer, the meat in the sandwich. And that creates our next big problem.
So we've done it. We've made photons. But there's a catch. They're trapped. They're born deep inside this chunk of semiconductor material, and they have to get out. But a stubborn law of physics called total internal reflection is standing in their way.
You've definitely seen this before. If you've ever been swimming underwater and looked up at the surface, you've noticed that at a certain angle, the water stops being clear and turns into a perfect mirror. That's total internal reflection, or TIR. And believe it or not, the exact same thing happens to the light trying to escape from the LED chip into the air.
Just how bad is this problem? It's a catastrophe. For a basic flat LED die, that escape window for light is so narrow that only about 2% of the photons we worked so hard to create actually make it out. The other 99%? They're trapped, just bouncing around inside until they're eventually absorbed as heat.
So how did engineers fix this? Oh, just through sheer genius. They started by shaping the LED die itself into tiny pyramids and hemispheres. Then they added those little lens-like epoxy domes you see on LEDs to help guide the light out. And now, they're even building these incredible microscopic structures called photonic lattices,
which are like perfectly designed little tunnels to funnel the photons to freedom. It's amazing stuff.
Okay, so our photons have escaped. We're done, right? Not quite. We have one more villain to defeat in our story, heat. Because even with all those improvements, LEDs still generate a lot of it. And heat is their absolute mortal enemy.
This is just a fundamental law of the universe, thermodynamics. You can't escape it. Every single process, every conversion of energy ultimately creates waste heat. And for a tiny little LED, managing that heat is the single biggest challenge in its design.
And the numbers here might surprise you. A modern high-efficiency white LED is only about 38% efficient at turning electricity into light. Now that's way better than an old incandescent bulb, but it still means that 62% of the energy you're pumping into it is completely wasted, becoming pure heat right inside that little chip. And that heat is so dangerous because of this vicious cycle called thermal runaway. See, as an LED gets hotter, its electrical resistance actually goes down. This makes it pull even more current from the power supply, which, you guessed it, makes it generate even more heat. If you don't stop it, this cycle just spirals out of control until the LED literally burns itself out.
So how do we stop this from happening? We need a hero, a silent guardian that can manage the power, protect the LED, and stop thermal runaway dead in its tracks. And that hero is the LED driver.
To put it simply, an LED driver is a self-contained power supply that's built specifically to control an LED. You can't just hook a high-powered LED up to a battery and cross your fingers. Without a driver to carefully regulate the power, it's just doomed to fail.
Now, the most effective kind of driver, the real brains of the operation, is a constant current driver. It's smart. It doesn't just supply a steady voltage, it supplies a steady, constant current. So if the LED starts to get hot and its resistance drops, the driver automatically lowers the voltage to keep that current perfectly stable, which breaks the thermal runaway cycle before it can even start.
And that's why choosing the right driver is such a critical part of any LED design. You've got to think about everything. What the LED needs, what your power source is, if you need special features like dimming. The driver isn't just an accessory. It's the brain of the whole system.
So yeah, from a tiny subatomic particle releasing a single photon, to the wild physics of helping that light escape, and finally to the intelligent electronics that protect it from destroying itself, the story of the LED is so much more complex and amazing than it looks. It's a marvel of physics and engineering, all packed into one tiny glowing sandwich.